Hi, this is Rocket. Welcome to Paper Deep Dive. Today we're going to talk about Elmo, with the full name Embeddings from Language Models. First, I would like to talk about advantages of Elmo over some traditional word embedding methods such as word-to-vec. Elmo would add contextual information into the word embedding. What I mean by this is, if we look at the example, Tom left his bank and went to the bank of a river nearby. In this sentence, we have two same word bank, but they have different meaning. One just means the actual bank they can deposit or withdraw money. The other just means the side of a river. The word-to-vec would give the same word embedding for those two word bank, but that's definitely not optimal. In Elmo, when we compute the embedding, it would consider the word before it and after it. So in this case, those two word bank would have different Elmo embedding, which is a better representation of the word. Next, I'm going to give an overview of the whole model architecture of Elmo. First, the input is a sequence of tokens, as I shown here from T1 to T3. And then each token will pass through a character embedding layer, which I'll talk more in the next slide. Then it comes to the core part of Elmo, which is the bi-directional bi-lstm layer. What this layer does is it would loop through all the tokens from left to right, and then from right to left. So from left to right is called forward pass, and from right to left is called backward pass. For each token, it would get a hidden representation in the forward pass and also the backward pass. This hidden representation contains contextual information, since it's computed by looping through the whole sentence in two directions. Also notice, there could be some small variations of this bi-directional bi-lstm layer. For instance, we can stack multiple bi-lstm cells on top of each other, as shown in this diagram. We can also repeat these whole blocks multiple times, in order to extract better contextual information. Elmo layer is pretty simple. It's just the weighted sum of all the hidden representations we computed in previous layers. Once we have the Elmo embedding, we can use it in other downstream tasks, and I just show it as other layers block here. When we compute Elmo, a standard downstream task is to predict the next word given the current word. For instance, if our input sequence is "How are you?", then the task would be given how, we want to predict are, given are, we want to predict you. Once we finish the training, we would fix all the parameters, and when we use Elmo, we would just tune the parameters in the downstream layers. That's all about the overview of Elmo. So as a quick summary, the input is a sequence of tokens, and then we have the character embedding layer, we have the bi-directional bi-lstm layer, we also have the Elmo layer. And during the training, we will just adjust parameters in those layers. And after the training, we would fix the parameter in those layers and only tune the parameters in the downstream layers. Now, we can talk about the character encoding layer. First, I would like to briefly mention some of the notations here. So B represents batch size, W represents the number of words, and C means the maximum characters per word. Let's say if we set C to 32, this means we can use at most 32 characters to represent a word. If the word has more than 32 characters, we would truncate it to 32. If the word has less than 32 characters, we would add padding and pad it to 32. The rest notations are kind of self-explanatory. I'll just mention it once we use it in this graph. Now we can talk about the diagram on the left. The input is a sequence of tokens represented in a matrix form. The first dimension is B times W, and the second dimension is C. This means our input is batch size number of words, and each word is represented using C number of characters. So this matrix is fed into a character embedding layer. This layer does nothing but adding a new dimension D at the end. So this is saying they embed every character using a vector of shape D. Also notice, This vector of shape D can be randomly initialized at the beginning, which means we just give a random embedding for each character. During the training, and because of the backpropagation, this embedding can be updated accordingly. After this character embedding layer, we have a bunch of convolution layers. We use Con1D here, which indicate they have one dimension of flexibility, and in this case is the kernel size. We illustrate this by using K1 through Km in this diagram. Each convolution layer with kernel size K is like extract K-gram information from the character embedding. To better illustrate this, we can see a graph. Now in this graph, we consider one batch and one word. So we would have a matrix of C times D, where C is the next number of characters, and D is the dimension size of each character embedding. So if we say we have a kernel size of 2, then it's like we create a window of size 2 times D. And this window would slide to the right every time until the end. So you can see this is like we extract a 2-gram character information while using a kernel of size 2. Similarly, if we use kernel size equal to 3, then it's like we will create a window of dimension 3 times D, and we just slide this window to the right and until the end. Something like this. So you can see with kernel size equal to 3, we are extracting the information of trigram. Also notice in convolution layer, we have a parameter called number of output channels. Let's say if we set this parameter to 4, this just indicates we need to use this small window and loop through the matrix from start to end 4 times, each time with a different initialization of the values in this window. Coming back to this diagram, now we can better understand the shapes of the convolution layers. If we look at the first one, the shape is B times W, C1, and D1. Mathematically, C1 is just equal to C minus K1 plus 1, since we extract K1 gram information from the character embedding, and we do this D1 times. For the rest of the convolution layers, we do similar things, and we have similar shape. After this convolution layer, we have a max pooling layer on the first dimension. This is saying for every K-gram we extracted from the character embedding, we only keep the largest value and discard the rest. So the shape would technically be B times W, 1, D1. But we can squeeze the first dimension and write it as B times W, D1. After this, we have an activation layer, which adds some non-linearity to the input signal. Some standard activation functions are ReLU and sigmoid, and they do the same thing for the rest of the parallel layers. All those signals are then fed into a concatenation and reshape layer. The concatenation layer will concatenate all the signals in the last dimension. So the shape of the last dimension becomes the summation of D1 to Dm. And this reshape layer will modify the shape from B times W to B comma W. Next, we have a highway layer. As shown in this slide, highway layer has skip connection and a dynamic gate. Let's say our input is X. We compute X projection by passing through a fully connect layer and then a ReLU layer as activation function. We compute X gate by passing through a fully connect layer and sigmoid as an activation function. And the final output, X highway, is controlled by the X gate. As you can see in this equation, 1 minus X gate comes from the original X, and the X gate part of it comes from the projection, and we just sum those up to get the X highway. The benefit of highway layer is that it can help with the faster convergence of parameters so that our model training will be faster. But if you think this highway layer is non-trivial, you can just think of it as an activation layer, because it won't change the shape of the input signal anyway. Coming back to this diagram, after highway layer, we have a fully connected layer, which changes the shape of the last dimension from the summation of D1 to Dm to capital D. At this point, for each word, we have a word embedding of shape D. That's all about the character encoding layer. As a summary, our input is a bunch of words with C number of characters, and we use convolution layers to extract n-gram information in the character level. And finally, we generate an embedding for each word with shape capital D. After talking about the character encoding layer, we can now jump to the bi-directional bi-lstm layer. Let's first go through the notation here. Capital B means batch size, capital W means number of words in a batch, and capital D means dimension of the word embedding. Small h is the hidden size of a bi-lstm cell, and capital L means number of bi-lstm layers. Going back to this diagram, because the hidden dimension of an bi-lstm cell is small h, once we pass the output signal of the character encoding layer to the forward pass bi-lstm layer, we would have an output shape of B, W, H. We then pass this signal into a fully connected layer to get a shape of B, W, D. And then we do the same thing for the backward pass of the bi-lstm layer. So we get another output shape of B, W, D. And we just concatenate those two to get an output shape of 2, B, W, D. As mentioned in the model architecture overview, we can repeat this bi-lstm layer multiple times. And in this diagram, I just repeated 2 times. This is also the same as the actual Elmo architecture. The output of the first bi-directional bi-lstm layer becomes the input of the second bi-lstm layer. And we do similar processing as before, and in the end, we have an output matrix of shape 2, B, W, D. And finally, we just concatenate the output from the character encoding layer, the first bi-directional bi-lstm layer, and the second bi-directional bi-lstm layer together. And to generalize better, if we set the number of bi-directional bi-lstm layer to be L, then the final shape would be 2 times L plus 1, B, W, D. That's all about bi-directional bi-lstm layer. As a quick summary, we use forward pass and backward pass to extract contextual information from the character encoding layer, and we concatenate all the signals together for the output. Finally, we can talk about the Elmo layer, which is nothing but a weighted sum of the output from the bi-directional bi-lstm layer. Recall that we have an output shape of 2L plus 1 in the first dimension, and 2L comes from the bi-directional bi-lstm layer, and plus 1 just comes from the character encoding layer, which is called the base embedding in the paper. And we just do a weighted sum of those to get the final Elmo embedding. That's all about Elmo introduction. Hope you like this video. In the next video, I'm going to walk you through the original paper of Elmo. See you next time.